Morning, everyone. So obviously we're remote. Hopefully you got to see the live lesson and you're just reviewing this to kind of go over the material again. But if you missed the lesson, please watch closely and then reach out if you have questions. I'll have available live sessions on Wednesday. Just sign up an adaptive scheduler and I'm happy to help. So basically, I want to pick up where we left off last week, where we were talking about if you have two equations, kind of how can you solve for their point of intersection without needing the graph? We talked about the basic version, which you should have seen last year anyway. And so now I'm going to take you to a new strategy known as substitution. So sometimes our equations aren't nicely set up in slope-intercept format. And so when we're solving for a point of intersection, we need a new strategy other than setting them equal to each other. So the big idea is notice how one of these equations here is already equal to a variable. In this case, it's already equal to y. And in this case, no variable is equal to anything. Everything's kind of mixed up. So all I'm going to do is say y is equal to all of this. And so in the other equation, 6y minus 12x. Actually, let me write this differently. So in other words, notice how I see a y here. And so I'm going to say, let's replace that y. Really, this means 6 times y. And so I'm going to say 6 times, and I'm going to leave a blank here. And all I'm doing is rewriting everything else. So the only thing I left a blank for was y. Because I have y is equal to something. Well, instead of y, I'm going to put that something. And I'm going to throw it in parentheses because that's going to be really important here. So once again, all I said is y is equal to this expression. And so in the other equation, I'm going to replace y with what it's equal to. Everything else is the same. And so now, notice how I have 6 times this stuff in parentheses. And so I'm going to do 6 times 4x, 6 times negative 5. And that's going to get me 24x minus 30 minus 12x equals 18. The reason substitution is useful is notice my only variable is x. I don't have a y anymore. And so I can actually solve for x. I can say, oh, well, this can still be simplified. Notice how we're on the left side, and I have a 24x and a minus 12x. And so really, that's going to simplify to just 12x minus 30 equals 18. I can now add 30 to both sides. And then I'll be left with 12x is equal to 48. And then finally, I can divide both sides by 12. And I'm going to wind up with x is equal to 4. All right. The nice thing about substitution is, remember, I'm asking for a point of intersection, which means I need x and y. But notice how one of the equations is already equal to my variable. And so I'm just going to say y equals 4x minus 5. But I just found out that x is equal to 4. So all I'm doing is saying, oh, if x is 4, then when I simplify everything out, I get that y must be 11. So my point of intersection is 4, 11. All done. All right. And so you can always confirm this. So if I take a look at a graph of those two equations, sure enough, you're going to see that they cross at the point 4, 11. So all I've done is proven using algebra and solving that I can get the same point of intersection without the graph. All right, cool. So now Let's take a look at a different case. So the only difference here is notice how one of the equations, rather than being y equals, is x equals. And so I'm going to do the same exact thing. I'm going to say, oh, I have x is equal to some expression, and I have an x in this bottom equation. So all I'm going to do is say that 5y is not going to change. But my goal is going to be to replace x because x is equal to this expression. So same thing as before, I'm just going to throw in this rectangle where the x used to be. And so once again, the 5y stayed, the 3 stayed. I left a blank where the x was, and the equals negative 13 stayed. And so all I'm going to do is now take this expression here. I'm going to throw it into my box, and I'm going to make sure to throw my parentheses around it. All right, and so now notice once again, y is my only variable. And so in this case, I'm actually going to end up solving for y first. So I'll distribute my 3 inside. So I'll get 5y. 3 times negative y will be minus 3y. And 3 times negative 9 will be minus 27. Cool. So now my goal is, if possible, can I simplify further? Well, on the left side of the equation, I see a 5y minus 3y. So sure enough, that can become a 2y minus 27 equals negative 13. And then I'm just going to solve like normal, plus 27 plus 27. Now I've got 2y is equal to, and just be careful here, negative 13 plus 27 is going to actually be a positive 14. And finally, divide by 2. And we get y is equal to 7. Cool. And so once again, I'm looking for a point of intersection. And so going back, notice how this first equation is x equals. So I'm going to put x equals negative y minus 9. Or, now that I know what y is, all right, this looks kind of weird because I just had this negative in front. Remember, whenever you just see a negative in front of a variable, there's technically a 1 hiding out there. And so really, this just means negative 1 times 7, which is negative 7. Minus 9, going to end up with x is equal to negative 16. And there you have it. But be careful when you write this. Notice how I solve for y first and then x. So just remember when you're writing your point of intersection, make sure your x value is always being listed first and your y value second. And once again, there you go. There's a point of intersection. And if you don't believe me, we can always verify. So I'll bring this graph back in. I have the 2 equations graphed. If I move over, sure enough, negative 16, 7 is exactly where they cross. All right. And then finally, I'm going to throw one more on for you. But what I recommend is that you pause the video right here and try to work this out yourself. Then, once you think you've got it all worked out, continue the video and verify that our solutions are the same. So at this point, pause, and then restart when you think you've got it solved. All right, so here, once again, I see x is equal to something. In this case, 2y plus 3. So since it's x is equal to something, I'm going to have to throw in for x. So now I'll have negative 4y equals 3 times something minus 29. Because remember, it's x equals, so x is going to get replaced in the second equation. That replacement will be 2y plus 3. Throw it in parentheses here. And I have my two sides. So I've got negative 4y equals, distribute that 3, 6y plus 9 minus 29. First goal is, can I simplify? I see a 9 minus 29. I can totally simplify that. So I'll get negative 4y equals 6y minus 20. Now notice how there's a y on both sides. I want to get y on one side. So I'm going to subtract 6y. Subtract 6y. It's going to leave me with negative 10y equals negative 20. Just make sure you're using your negative here. So I'm going to divide by negative 10. Divide by negative 10. And I'll get y is equal to positive 2. All right, and then I'll take a look. I already know x is equal to 2y plus 3. I solve for y, so I should be able to replace y. And 2 times 2 is 4, plus 3. I should get x is equal to 7. And therefore, my point of intersection is going to be 7, 2. All done. And one last verification. Let's check the graph. Let's make sure I'm right. Sure enough, 7, 2. And there you have it. So once again, please let me know if you have questions.